Hi friends, let's discuss about heaps today. So there are two types of heaps. One is max heap and another one is min heap. So in the max heap, the parent element always greater than or equals to the children's, just immediate children's, okay? For example, for 97, 96 and 90 is the immediate children. Similarly for the 85, 53 and 82 is the immediate children. So for 53, 28 and 33 is the immediate children. So always the parent node value is always greater than its children. So if that property is satisfied, we call it that as a max heap. As many of you know, heaps are stored in arrays rather than creating using struct nodes. Okay. For convenience, we will leave the index 0 and we will start from 1. Okay. So the children of index I will be stored at index I star 2 and then index of I star 2 plus 1. For example, for 1, 1 2s are 2, 1 2s are 2 plus 1 3. So at index 2 and 3, the values of its children will be stored. Similarly, for example, if we take index 6, so 6 2s are 12. And 6 2s are 12 plus 1 13. So at 12 and 13, the immediate children of index 6 will be stored. Similarly for this, if you take index 10, so children of index 10 will be stored at 20 and 21, so and so forth. Okay, so that's about the heaps, in particular max heap. Okay, let's create and see in a visualized form how the max heap will work. Okay, let's create one fresh max heap, say for example with the element 4. So because there is only one element, it will be stored at index 1. As I said, like index 0 will be ignored and values will be stored from index 1. Now let's say I want to insert value 30. So value 30 will go first to the index 2 and then it will be compared with the parent. If the value is larger, I mean the value at the parent is smaller, so it will be swapped as you see here. So this is called percolate up. So we have 30 initially at 2, index 2, because the 30 is greater than value 4, which is at index 1, the parent. So they both will be swapped. So we are like moving the values from the bottom to the root. So this is called percolate up. So normally during the insertion we will perform percolate up operation. So let's insert one more value, let's say 71 for example. So at 3 it will be inserted, again percolate up will be performed. So 71 will go to the parent node. Now let's insert 67 for example. Now the next available index is 4, so at 4 it will be inserted and then percolate up will be performed, and now as you see it got inserted at 4 and percolate up performed. So it came to the root, that is index 2, but then from index 2 to 1 the value is already less, so there won't be any percolate up here. So leaves 67 will stay at index 2. Now let's do one more operation, one more insertion, say let's 3, and because the next available index is 5, so it will be inserted at 5th index, and then it will perform percolate up, but because 67 is already greater than 3, so it won't do any percolate up, it will just stay as is. Okay, great. So this is the typical insertions. So during every insertion we will put the value at the last available index. That is, for example, next value will go at index 6, and then at index 6 we will see what is the root. So root always comes by dividing the index by 2. For example, the index 6 root will be at 3. Okay, similarly index 5 the root will be at 2. So the floor value we have to take. So 5 by 2 is 2. Similarly 4 by 2 is 2. So for both 4 and 5 the index is at 2. Similarly for 2 and 3 the index will be at 1, because 2 by 2 is 1 and 3 by 2 is also 1. So we will find the root and then we will compare the values at the children and the root. If they are children is larger than the root, then we will swap. So we call that as a percolate up operation. Okay, so let's code this and see how the things will work at our code. Okay, let's go back to our code panel. So here let me take one max heap with values 100 and then last index. So let's store it as a 1 and then operation and then element. You will see what is this operation and element. So I will do one do while loop. So while operation not equals to -1. So we keep on ask for the operation. So operations are something like this. Print operation operation. Okay, so 1 is for insert, 2 is for delete, 3 is for print. Okay, so we will have one switch operation. Okay, so case 1 will be insertion, so we will write to the logic, but for now let's have the cases, all the cases. Okay, so now let's fill the case 1, that is for insertion. So for insertion we need the element, so let's take the element from the user, enter the element to insert. Okay, so let's read this into element. Okay, now we have the element in our hand, so we have to insert. So we always should look into the last index, available index. So we have to first insert the value into the last available index. Okay, so let's put it blindly, and then we have to do the percolate up. So we have to compare with the root. If the element at the root is smaller, we have to swap. So that's what I will do. So while let's take one temporary index. Okay, let's declare this as well. Index. Now the index, while index should be greater than or equal to 1, and the element at the max heap, element at the root. So how we will get the root value? So index by 2, right? So that should be less than max heap at current index. So if that is so, we have to swap. So let's take one temporary variable. So this is just the swap logic. We swap the element at the child and the parent. So at the end we have to update the index, because we are doing the percolate up, so index will always keep decreasing from the child to root. So we have to do this till up to the index is greater than or equal to 2. Okay, so at the end what we have to do, we have to increase the index by 1, right? Because we have inserted, so the index should be greater than, it should be increased by 1. Okay, let's quickly write the print logic as well, printing the heap. So great. So let's do this insertion and see how the max heap looks like. Okay, let's run it. So operation ID will be 1, so I will be inserting value 4, and then again 1, this time 30, again 1, this time 71, again 1, this time 67, again 1, this time 3. So let's try to print. Okay, so this should exactly match with the heap I have just now created. So 71, 67, 30, 4, 3, 77, 67, 34, 3. So it is exactly matching. So we are done with the insertion operation. Okay. Now let's do the deletion. So deletion is a little tricky. So that I will explain. Okay. First let's go and see visual way of deleting the element from the heap. In particular max heap. Okay. So let's say for deletion we have to pass the index. Say let's give 2. So I want to delete the value at index 2, that is 67. So the first step it does is it will take the max value in the heap, which will be always available at index 1. So it will take one value higher than the max value, so that is 72. So it will keep the 72 here. Okay, and then it does the percolate up operation, because 72 is the next now currently available max value, so it has to be percolated up. So 72 will go as long as it should be. So in this case, because this is the highest value, so it will always go to the root. So 72 will come here, 71 will come here. During the percolate up we will swap. Then because it is already reached to the root, we will stop there. So after the percolate up, the configuration will be something like this: 72 will be here, 71 will be here, rest of the values will be intact. Once we do that, next thing we have to do is, second step is, after the percolate up, second step we have to do is take the last value, that is 3, which is available at index 5. Take that value and keep this value at the root. So in the root we have 72, so that will go away. So 3 will be kept here, and reduce the heap size. So heap size will be now only 4 values, 1 to 4, because this is lost. In a way we kept it here. So because we kept value here and we don't know the exact place of this 3, so we have to do percolate down. So percolate down means again it will be compared to 71 here and 30 here. So because 71, 30, which one is the larger? 71 is larger. So 71 will go again up and 3 will come here. And then 3 and 4, because only child is 4, so 3 will be compared with 4. So because 4 is larger than 3, so again these two will be swapped. So finally 4, 3 will come here. So after the deletion, what is the configuration will look like? 71 will be here, 4 will be here, 3 will be here, and 30 will be intact, and this node will be deleted. Okay. Okay, let's see that in visual way. Okay, I'm doing the go. So first step is we have to put the value, max value plus 1 at the deleted index. So it will be 72. So it will keep the 72 and then does the percolate operation. After that it will take the last available child index and that value, and that value will be taken and kept it at the root and does the percolate down operation, which will take the 3 into this position. Okay, let's observe carefully. I'm doing deleting, so it is 72. Again it will does the percolate up. Now 3 will go and reset at root, and 3 will be percolated down. So this is the final max heap configuration after the deletion. Okay, let's do the same thing in the coding. Great. Okay, so first we have to read the index to delete. Okay, let's read it into index. Index we already have. Okay, now what I said is, first we have to, at the index we have to keep the max heap value plus 1, right? Where we will get the max heap value? So max heap value will be available at index 1. So let's take that and do the plus 1 and update the value. Now we have to do the percolate up, right? So here we have already done the percolate up operation. Let's take that as is and paste it here. So while index is greater than, index less than, so everything remains same. So this will make sure the percolate up is done. Okay, now what we have to do in the second step, we have to take the last value and keep it at the root, right? So that's what I'm doing. Max heap will be max heap of 1 will be max heap of last index minus 1, because last index will be always pointing to the last value plus 1, right? So we have to reduce by 1. Okay, and definitely we have to decrease the heap size. Now we have to do the percolate down operation. Okay, now we kept the minimum value, so in this case 3 we have kept it here, so we have to move the 3 to the towards the leaves, such that it always satisfies that max heap condition, that is parent node should always be greater than to its children, right? So let me do that percolate down operation. So in the percolate down operation, we have to do something like this. So here index will be starting at 1 at the root, and we have to come to the last, so it should be less than last index, right? And then here while percolating down, we have to first see are the values at the children nodes is greater than this value, right? So let me write one method which will find max value. Okay, I will pass the index, current index and last index, and then of course max heap we have to pass. So it will return, let's say it returns one temporary index, and say it is -1 initially. So here so what it does, it will check the children of this IDX index. If they are larger, any one of them, if they are larger, it will return the index of the larger value. Okay, so great. So if this is, and if there is no children, or if there are children but the values are already less than this root, so that case it will return, this method will return -1. So we have to check if there are children and their children are greater than the parent, then we will get the proper positive index, otherwise we will get the minus index, -1. Okay, I haven't written this method so far, but we will write. Okay, and yeah, let's now do the same percolate down operation. Okay, so percolate down operations will be performed at, the swap should be between index and temporary index. Okay, and then index will become temporary index. Great. So that's it. This will does the percolate down. Now let's write the find max. Okay, so it will return some index, so find max, it will take the index, it will also take the last index, and then of course we have a max heap. Okay, so let's write it. Yeah, so first compare index star 2, which is the first left child, is less than last index, right? And index star 2 plus 1, that is the right child, less than last index. If so, so there are both the children available for this node, or this for this index. Okay, in that case we have to see if max heap of id star, yeah, because both the values are available, we have to take the max of those, right? That's what I will do here. If this is the so, we have to return, because index star 2 plus 1 will be max, so we have to return index star 2 plus 1 we have to return, else we have to return idx star 2, right? Okay, great. For example, both the indexes are available, I mean both the children are available, and here we have seen directly comparing which value is less than I mean both the children, out of both the children's which value is the max. We are blindly returning that. Actually we shouldn't do that. We should compare with the root value. If that value, the max value among the children, if that is lesser than the index or the parent, that time only we have to return the proper index. So we have to do let me take one more int temporary index, let's say -1. So let's fill this as a like this. Okay, and yeah, now let's compare if value set max heap idx less than max heap t idx. Okay, if max heap is less than the means children are larger than the parent, so that case only we have to return temporary index, otherwise we have to return -1, because there is no need to do the percolate down operation, so we can stop it here. Great. So let's take one more case. Here this case covers when both the children are available. For example, say there is only one children, so definitely that is a left child in the heap, because we will fill the values from 1 2 3 4 5 6 7 like that. So it is always the left child will get filled first, followed by right child. So because there is no right child, if this condition is not satisfied, means there is no right child, so there is a possibility of we still have the left child. So let's do that. If this is the case, okay, now we have to again compare if max heap of idx less than max heap of idx star 2. If the parent node is less than the children node, then we have to return idx star 2, otherwise we have to return -1. And finally, if none of the conditions are met, we always have to return -1. So this is the logic for finding the maximum element among the children. Of course, it will also find the maximum element among the children, and also it will return proper index if the children value is larger than the parent, otherwise it will always return the -1. Okay, let's try to run and see what is the output. I hope it should work. Let's see. I will do the same way of I will do the insertions in the same order. So it will be 4, then 30, then 71, and then 67, and then the value 3. So let's print them. Yeah, they are correct. Now let's try to delete value at index 2, that is 67. Index will be 2, and yeah, it got deleted. And let's try to print and see what is the output. Yeah, 71 4 33. Is it matching? 71 4 33. So yeah, so that's it, guys. Deletion is also working fine. I hope the code is clear, and if you still have any doubts, please leave a comment. I will try to answer you guys. Great. Okay then. Chalo. Thank you guys. Bye bye. See you in the next video.